Hi everyone. Today we're going to talk about higher order derivatives. So before we start doing that, let me just remind you what a derivative of a function was. So as you remember, the derivative of a function is defined as the following limit here. It's given in this formula, right? So what's the second derivative? So the second derivative is the derivative of the first derivative. So remember that the derivative was nothing else but this limit, so it's a function of x. So now we're taking the derivative of this function. So using this, using a formula, we can write that the second derivative, which is denoted by the f2 primes x, so we say f double prime x is the derivative of the first derivative, so this formula here, okay? So similarly, we can talk about the third derivative of the function, and that's going to be the derivative of the second derivative, which is defined above. So the third derivative can be written as this equation here. So the third derivative of a function is the derivative of the second derivative. Okay? Similarly, we can define the fourth derivative, fifth derivative, and any number you want. You can define 100th derivative. In general, for n plus first derivative, we have to show the n plus first derivative is defined as the derivative of the nth derivative. So we have, for instance, I don't know, we want to define 100th derivative, that's the derivative of the 99th derivative. So we have a lot of different derivatives. So why do we do that? Well, first of all, in some situations, in applications, it's important to find out the second derivative. For instance, the second derivative has a very natural interpretation as acceleration. So when you're driving a car, when your velocity is increasing, that means the derivative of the velocity is positive. So what that means in terms of acceleration, it means your acceleration is positive. So you're accelerating, meaning that your velocity is going up. If you're decelerating, that means the second derivative is less than 1, less than 0, or acceleration is negative. That means your velocity is decreasing, right? So you're slowing down. So that's the meaning of the second derivative. So the second derivative of the distance is just the acceleration. Or if you want to talk about it differently, is the rate of change of the rate of change, right? So the rate of change of the rate of change of the distance. So what's the rate of change, the regular rate of change when you're driving? That's the velocity or the speed. And when you're talking about how fast that's changing, that's already the acceleration. So if this is a little bit confusing, hopefully the examples will make it more understandable. So next we're gonna do several examples calculating the first and second derivatives of a function. So the first example is to calculate the first derivative of this function, which is just a polynomial of degree 3. So it's polynomial of 2x to the power 3 minus 2x squared plus 1. So the first derivative is, of course, we can find using just 2 times the derivative of x to the third, which is equal to 3x squared, minus 3 times the derivative of x squared, which is 2x, and the derivative of 1, well, 1 is a constant, so the derivative of 1 is 0. So our derivative, if we simplify, becomes 6x squared minus 6x, okay? So the second derivative is nothing else but the derivative of the expression of the derivative. So the expression we just obtained. So the second derivative is the derivative of the first derivative, which means the derivative of this expression from the top. Okay, so that means we have to take the derivative of 6 times x squared, so that's 6 times 2x, minus 6 times the derivative of x is 1, right? So that is 2x and this is 1. So if we simplify, that becomes 12x minus 6. So in all these cases, I'm just using mainly the power rule, which, if you remember, of course, is saying that the derivative of x to the n is equal to n times x to the n minus 1. Okay? So next example, here's next example, is also a polynomial. Now it's a polynomial of degree 4. So the first derivative is obtained the usual way. So you take the derivative of t to the power 4 minus 2t to the power 3 plus 6t squared minus 3t plus 10. So we take the derivative term by term, and what we obtain is 4t to the power 3 minus 2 times, so the derivative of t to the power 3 is 3 times t squared. Derivative of t squared is 2t, and derivative of t is 1. And the derivative of 1 is 0. Simplifying, we obtain this expression here. Okay. So next we want to find the derivative of the first derivative. So that's the second derivative. We want to find this. So that's going to be the derivative of this green expression from above. So to do that, it's just a polynomial. So then we have 4 times t to the power 3. So t to the power 3 gives us 3t squared. 6 times t squared, so t squared, the derivative of t squared is 2t. Derivative of 12t is 12 because the derivative of t is 1, and the derivative of 3 is 0. So that's just going to be that. And if we simplify, we're just going to get this expression here. Okay. So next, example 3. So this is a bit different. It's not just a simple polynomial. It's a function which is written as a product of two polynomials, right? So we can, one of the ways would be, of course, to like write it out as a polynomial, but then it would be much too complicated. Instead, we decide to we're going to use the product rule. So we have two expressions, two terms here, which are we are multiplying. So we're going to use the product rule. The first term is going to be x squared plus 1. So that's the first term. That's our u here. And the second term is x minus 1. So that's going to be this term here. So the derivative of so that's our second term. So u and v. So then I have u prime, which we calculate here. So what's u prime? Now let's look at u. U is equal to x squared plus 1 squared. So in order to calculate the derivative here, we have to use the chain rule, right? So I can just write that down. So we're using here the chain rule to calculate the derivative. So that gives me the derivative of the outside function, which is the x squared is the outside function. So the derivative gives me 2 times whatever is inside times the derivative of the inside function, and the inside function is x squared plus 1. So the whole thing becomes 2x squared plus 1 times the derivative of x squared plus 1 is, of course, 2x. So if I just simplify the whole expression, I get 4x times x squared plus 1. So that's just the derivative of u. Okay? So that's the yellow part here. So then the derivative of v is x minus 1, and of course the derivative of v is equal to 1. So now we're going to use these two things to find out what's the derivative of h. So we're going to plug these two things that we obtained, this one here into the product rule. So we're going to get the first u prime, so that's what we're using, 4x times x squared plus 1, that's what we plug in here, times v, which is x minus 1, plus x squared plus 1 squared, times the derivative of v, which is the derivative of x minus 1. So it's equal to 1. Okay? So what do we do now? We can factor out, so here I wrote, we can factor x squared plus 1 out, because both of this expression have x squared plus 1. So if I factor it out from the first term, I'm going to get 4x, which is this term here, and x minus 1, so that's there. Plus, and from the second term, I'm going to get x squared plus 1 square. If I factor x squared plus 1, there is one more x squared plus 1 remaining. And then I simplify this expression in the parentheses here, and what I obtain is x squared plus 1 times 4x squared minus 4x plus x squared plus 1. I combine the similar terms and I obtain the answer in this red frame here. Okay? So next we're going to calculate the second derivative of h, which means the derivative of this expression from above. Okay, so that expression from above. So, and we're going to use the product rule again. So I'm going to write here. So we're going to use the product rule. So let's see. So what's my u? So this term here is going to be my u, and this term here is going to be my v. So u is equal to x squared plus 1. So therefore the derivative of u is just 2x. That's what we have here. And v is equal to this equation, 5x squared minus 4x plus 1. So if I differentiate, I'm going to get 5 times 2x minus 4, because the derivative of 1 is going to be 0. Derivative of 4x is just 4, so the whole thing is going to be 10x minus 4. Okay, so then I'm going to use these two things to with the product rule. So if I calculate now the derivative of this expression here, so that's going to be the derivative of u, which is 2x times v, which is this thing here, plus derivative of, well, u, which is x squared plus 1, times the derivative of u, which is 10x minus 4. Now, let's look at this from here. So if I might multiply 2x throughout these parentheses and do the FOIL in this second pair, so I get this expression here, right? So 2x times 5x squared minus 2x times 4x plus 2x times 1 plus x squared times 10x. So then I have 1 times 10x minus x squared times 4 and minus 1 times 4. Okay, so those are all terms. I'm going to simplify and then collect similar terms, which I underlined with the same colors. So here I have 10x squared and 10x squared. That gives me 10x to the third, 10x to the third here. So that gives me 20x to the third, and I have similar things for the rest of the terms. So then I see that 4 is a common factor, then I'm going to factor it out, and that's what I get as an answer. Okay, so hopefully that makes sense. So again, all I have to do is to use the product rule in both of these um, derivatives. So both for h prime and h double prime, I had to use the product rule. So the next problem is problem 4, which is to find the derivative of this function h given here. Okay. Now this looks like a complicated function, but we can simplify quite a bit if we note that this expression inside here is nothing else but w plus 2 squared. Right? So I have it here. We have that the w squared plus 2w plus 4 is nothing else but w plus 2 squared. Just remember the formula, which is a plus b squared is a squared plus a squared plus 2ab plus b squared. So if we use a equals to w and b equals to 2, we get exactly the same expression on the right hand side here as what's inside of this parenthesis here. Okay, so therefore we can write this whole expression as w plus 2 squared to power 5 quarters. Now we can simplify this by noting that 2 times 5 quarters is nothing else but 5 halves. We know that when we're taking a power of a power, the powers multiply, so this 5 halves is nothing else but 2 times 5 quarters. And therefore we have to take the derivative of this expression here, which is much easier than the expression we had before. Okay, so now to take the derivative of this expression w plus 2 to power 5 halves, we have to use what? We have to use the chain rule. Okay, so why do we have to use the chain rule? Because we have a composite function where the inside function is w plus 2 and the outside function is x to power 5 halves. Okay, so we have that the derivative is equal to the derivative of the outside function, which by power rule is equal to 5 halves times this expression to power 5 halves minus 1 times the derivative of the inside function. Well, but the inside function here is w plus 2, right? But the derivative of that is nothing else but 1. Okay? And here I have, I made a mistake here, of course, and this t is not supposed to be t, but it's supposed to be w. And similarly here. Okay? Okay. So now, so we get that this is equal to 5 halves times w plus 2 to power 3 halves. Okay, so that's the first derivative. To find the second derivative, we have to use the chain rule again. So it's very similar to the previous thing. So we have 5 halves times the derivative of this expression here, right? This expression there. So that's equal to, again by chain rule, it's equal to 3 halves times this expression to power 3 halves times minus 1. Then we have to multiply by the derivative of w plus 2 prime, which is the inside function, but that's equal to 1, so that's why I didn't write it down. So the whole thing becomes 5 times 3 here on the top is 15, 2 times 2 is 4, and then I have w plus 2 to power 1 half, which is this expression. So 3 halves minus 1 is 1 half. So that's our answer, the second derivative. Okay. So the next problem is this one here. So we have to take the derivative of this expression and the second derivative. So of course we have to use the quotient rule. So by quotient rule I have the top is equal to x and the bottom is equal to 2x plus 1. So by quotient rule it's the derivative of the top times the bottom minus the top times the derivative of the bottom. Okay, and divided by the bottom squared. So that's equal to the derivative of x is 1 times 2x plus 1 minus x times the derivative of 2x plus 1, which is 2. So that's the top here. And the denominator stays the same, doesn't change. So if I simplify the top, I'm going to get 1 times 2x plus 1. So it's 2x plus 1 minus 2x. 2x cancels 2x. And then I have 1 on the top divided by 2x plus 1 squared. Okay, so that's my answer for the derivative of this function. So for the second derivative, I have to take the derivative of the first derivative. So the first derivative is this, the green thing here. And now I have to take the derivative of that. And the derivative of that is, well, how do we find that? Let's write it as 2x plus 1 to power negative 1, negative half, negative 2, because I have this thing here in the denominator, right? 2 becomes negative 2 when I move the whole thing up. So I have to use the chain rule again, okay? So the chain rule tells me that it's going to be the derivative of the outside function, which is this, right? The outside function is x to power negative 2, so it's going to be negative 2 times this expression to power negative 2 minus 1 times the derivative of the inside function, which is 2x plus 1. Okay, so the derivative of 2x plus 1 is of course 2, because the derivative of 1 is 0, and the derivative of 2x is just 2. So the whole thing becomes, if I multiply this negative 2 and 2, I get negative 4 times 2x plus 1. Okay, so that's the second derivative of my function f. So next one is very similar, so I'm going to skip this probably because it's very similar. The only difference is I have a power 1 half instead of negative 2 like in the previous example. Okay. Next, we're going to do problem 7. Problem 7 asks to find the third derivative of the function below. Okay, so this is the function, and we're going to take the derivative of that function. Okay, so let's take the derivative. It's going to be 3 times 4x to the third minus 4 times 3x to the squared. So it's going to be 12x to the third minus 12x squared and I can factor 12 out, so it's going to be 12 times x to the third minus x squared. The second derivative here is equal to the derivative of this expression here of the first derivative, so I can find it just like before using the power rule again. And finally, the third derivative here is the derivative of the second derivative, which we just found, and it's equal to 12 times the derivative of 3x squared minus 2x, right? The derivative is equal to that, right? Just by the power rule. So derivative of 3x squared minus 2x is equal to 3 times 2x minus 2 times 1. That's just 2. So I can factor the 2 out, or, well, if I just simplify, I'll get 6x here. And if I factor 2 out, I'll get 3x minus 1 inside the parentheses, so the whole thing becomes 36 times 3x minus 1. So that's the third derivative of my function. For problem number 8, well, we have to take the third derivative of this function here. So, well, let's start with the first derivative. So the first derivative, because this is a composite function, so we have the inside and outside. So the inside is going to be this. So that's the inside. So derivative of the inside, which is equal to 1/2 times derivative of t squared is 2t, right? So minus the derivative of 1, which is 0. So if I calculate that, that will be equal to t. And then the derivative of outside function, we just find it using the power rule. It's 5, it's saying 5 here, times 1/2 t squared minus 1 to the power 5 minus 1. Okay, so that's what we get with the chain rule combined with the power rule. So then if we simplify, we're going to get 5 times 1/2 t squared minus 1 to the power 4 times t. So it's equal to this expression here. Okay. Next, we're going to take the second derivative. So that means we have to take a derivative of this expression here. Okay. So the derivative of that. So that's what we have here. Now, what is this? This is a product of t. This is the product of t and this expression here, right? So we're going to use the product rule. So here is what I'm doing. So I'm taking q equals t and v equals to that. So the derivative of u is of course 1. And the derivative of v, we have to use chain rule to find it out. So it's going to be 4 times, so that's this 4 here, this 4 here, times the expression inside to the power 4 minus 1 times the derivative of the inside. That's the derivative of the inside. So the whole thing becomes 4 times 1/2 t squared minus 1 to the power 3 times the derivative of inside is just t. We just calculated it before on the previous problem here. Okay. So if we simplify everything, you're going to get that the derivative of v is that. So now we can use the product rule. So the product rule tells me that it's going to be u times v. So this is my u, oh sorry, u prime times v, right? So plus u times v prime. So then I have um, well, u prime is 1, and I have v, which I just copied, plus t times, and the derivative of v is this expression here. Okay, this expression here. So if I simplify, I'm gonna get 5 times. Now note that there is 1/2 t squared minus 1 to power 3 here, and 1/2 t squared minus 1 to power 4 there. So we can factor the 1/2 t squared minus 1 to power 3 out. So that's what I did here. And what's left is, well, there is one more because there's 4 of them here. So there is one more of 1/2 t squared minus 1 left plus 4t squared. Why did I have 4t squared? Because I have 4t and another t here. And so if I simplify this expression, I'm going to get this exactly. Okay. So that's the second derivative. Okay, so for third derivative, we have to take the derivative of the second derivative. So here is the second derivative, which we just calculated. So we have to take the derivative of that expression, right? And so we have to use the product rule. So we're going to use u as the first term here and v as the second term here. So here I have u is equal to 1/2 t squared minus 1. So the derivative of u is equal to t after simplifications. And then v is equal 4.5 t squared minus 1. So the derivative of v is 4.5 times 2t by the power of, right? So it's the derivative of t squared minus the derivative of 1, which is 0, so that's why I didn't write it. So the whole thing becomes derivative of v prime is equal to 19. So we use these things and plug so into this expression. So you get 5 times u prime, so that's the derivative of u, which is t, times v, which is this expression here, plus u times the derivative of v, which is what we have calculated here. So if I simplify everything, I get 4.5 times t to the power 3 minus t times 1 plus 1/2 times 9t squared. So 1/2 t squared times 9t. So that's 4.5 times t to the power 3 minus 9t times 1. Okay, so that's what I get. Now I combine the similar terms. So the terms which contain t to the power 3, I combine them and I get 9 t to the power 3, and then I combine the terms which are of the form a constant times t, so I get negative t minus 9t, so I get minus 10t. Okay, so finally I can factor out, so I can leave the answer as is here, or I can factor all common t, so there is a t here and there is t to the power 3 here, so I can factor one of the t's out, so I get 5t times 90 squared minus 10. Next, we're going to do problem number 9. This is a word problem, so I'm going to read it first. So, during testing of a certain brand of air purifier, the amount of smoke remaining as a percent of the original amount, T minutes after the start of the test was given by the following function. So the function is given as a polynomial of degree 5. We need to compute a prime of t and a double prime of, actually a prime of 10 and a double prime of 10. So this is supposed to be 10. And interpret the results. Okay, so we're going to calculate the derivative of this function here, this polynomial. Okay, it's a simple polynomial, so the derivative is equal to negative the constant times the derivative of this expression here, t to power 5, which is by power rule is equal to 5t to power 4, plus a constant 0.00468 times derivative of t to power 4, which is 4t to power 3, and then similarly a constant times the derivative of t to power 3 plus another constant times the derivative of t to power 2, and then you have a negative 17.63 derivative of t, which is 1. So there's a 1 there, plus, and the derivative of 100 is just 0 because 100 is a constant. So if we simplify the expression, we get this expression below. So this expression below is just simplification of the one from the previous line. And next, I plug 10 into the expression from the previous line. So I just plug 10 instead of t, and I get 10,000 instead of t to power 4, 1,000 instead of t to power 3, 100 instead of t squared, 10 instead of t, and then there is nothing for the constant term, and after a calculation I obtain a number. Okay. So similarly, I need to find out the second derivative. So in both of these problems, it's important. First, you have to find the derivative for every t, and then plug the appropriate value of t. So again, the derivative is going to be equal to the second derivative is equal to the derivative of a prime, and a prime is given by this expression here, of course, the one here. So I'm taking the derivative of that expression. So again, now I'm going to do the derivative of a constant times t to power 4. So that gives me 4t to power 3. A constant times t to power 3. So that's a constant times 3t squared. And then a constant t squared gives you the derivative is equal to 2t. And then you have the linear term, which gives you a constant. So I have here times 1, if you wish, minus the derivative of this term here gives you just a constant. It gives you just 0. So if I simplify, I get this expression here. Okay, finally I need to plug 10 instead of t, and I get an expression which I can just do the calculation and find find out what that is. Okay, so to interpret our results, we need to understand what's the meaning of uh, a prime being negative and a double prime being positive. And a prime negative means that amount of smoke is decreasing, and a double prime of 10 being positive, it means the rate at which this amount of smoke is decreasing is positive. So that means the amount of smoke is becoming smaller and smaller at an increasing speed. I hope I'm glad, Daddy, because I'm all done. Okay, thank you. I can read